Let me start recording. Hi, everyone. It's exciting. Yeah, my mom said it was 84 in Dallas yesterday. I was like, I don't want to go to 84 degrees. Like, I wouldn't mind going to 65 degrees. Anyways, all right. So, by the way, I did post the exam last night. Here's the exam. It says here it is. I made it due next Friday instead of next Thursday night. I made it due next Friday at 5, just because I didn't post it till last night. I was fretting over it. I also did update the exam info page a little bit just to, like, here's the exam. And then I did write, I mean, there's instructions on the exam, but I also said, like, you don't turn in that first attempted feedback. I was still liking the idea of you taking it for a few hours, just without notes and books and stuff, just to see how you can, you want to test it against yourself. So I think, yeah, I would like you to still do that. And then I know, yeah, I'll let you know my office hours specifics soon. I'll post them over the weekend sometime. And then I think I just put the same kind of instructions here, just like the block off a few hours, take the exam just to see how that goes. And then once you do go to, like, talking to people, make sure you cite and write up nice solutions. And I'll post the feedback for your write-ups for the first midterm over the weekend so that you can actually see whether I thought you were writing up nice things nicely enough in the first place. Okay. So, all right, good. Good. And then today we're going to talk about this thing called Green's theorem. I don't want to spoil it too much. So I'll come back to the handout on Green's theorem. But I do want to pick up where we left off end of class last time, where I was showing you vector fields that had curl, where the little flywheels would start spinning when you dropped it in the vector field, right? And we talked about, let me just try to write some of this down. I was sort of saying things, oh God, I didn't make it what I want. Take me off the screen, okay. Yeah, so, right, so let's talk about circulation and curl. Curl, and well, I'm going to say that we're going to talk about something called Green's theorem, but I would like it to be a little bit of a story, so I don't just tell you what it is, but we sort of see it fall out of some stuff. So this is all in 2D. This is all in 2 dimensions. This whole story. So F, we have a vector field, which I'll write, as a function pi plus another function q times j. And C is a closed loop in the plane. So it's just some closed loop like that. And we're going to orient it counterclockwise. That's just the convention. Oriented counterclockwise. Okay, so what we said is that what we've seen so far is if q sub x equals p sub y, remember these crossed partials are equal, right? We differentiate this with respect to x, we differentiate this with respect to y, see if they're equal. If they're equal, then f is path independent, and so it's actually circulation free. Is path independent slash conservative slash is a gradient field slash circulation free. let me just use the term circulation free, i.e. the integral around C, this closed loop, maybe I'll use this little circle over around the integral, which I said sometimes people write when they do integral around a closed loop, is 0, right? So circulation is 0. Yeah. And then we also the thing we sort of noticed last time is this also means if we had a little tiny closed loop. So, this is really any closed loop in the plane, or at least where this, is working. But we can think about like a tiny closed loop. So like, something small where we've put, I don't know how to draw, like a little flywheel, but we put like a little flywheel. I guess that applet had these little like thing here. So there's no net like angular momentum sort of thing imparted, right? There's no net force. So this doesn't spin. So these don't spin. Won't spin, right? That's when we saw those little pictures of the little jacks in the applet spinning. Those won't spin. So also we say that, so we call this the curl equals 0. Yeah, Sarah. I just mean you put a tiny closed loop anywhere in the plane, right? Maybe I should show the applet thing again, like, it's a little bit, I wish I could make them, sorry, we had like, it's a good one that's actually conservative. Let's just do like a, oh, okay, let's just do this one, I think. Oops, what am I trying to do here? I want to show curl detectors. So I wish I could hold these jacks in place, right, instead of having them move. But if you hold them in place, you can think about putting a tiny loop there as a path, and then the circulation around that path would be 0 because so that's not going to spin. Does that make sense? Yeah. That's right. That's right. And I haven't, I want to define curl in a more rigorous way. Right now I'm sort of saying the little thingies don't spin if there's no curl. And if there is curl, they spin. Like I think we saw, I liked this one here, that these do spin, right? They do turn, they do rotate. And here the curl is not, so that's non-zero curl. Oh, so I'm not showing the first off, okay. Pin myself and then, yeah, here. Yeah, these things are spinning, right? Slowly, but they're spinning. And I think I was also showing you at the end of class last time, like maybe if oh, hello. Those aren't spinning. If I did like 7y, nope. Wait, I want 0, 7y or something like that. Whoa. Oh, that's not what I wanted. Oh, let me slow that down. Those spin, and they spin a little faster than if I just did, well, now this, it's kind of hard to tell because the field's moving slower, but they're also spinning more slowly. So so that you can have more and less curl. You can have the thing spinning pretty rapidly, or you can have them just turning very slowly, right? And so you can kind of think about as the circulation at a point, like there's some sense of like, what's the circulation at a point, right? So maybe we should think of curl as circulation at a point. but let me just say, I'll get to that in a second, but if Q sub X is not equal to P sub Y, then we still could have the odd, the sort of random closed loop line integral be 0 if we just choose things correctly. But in general, you can't assume no circulation. So not 0 usually. And so the curl, which is like circulation at a point, is non-zero. And we've sort of seen that with some of these examples. So the little things spin. The little flywheels. Little flywheels spin. Okay, that's the way we're saying it. But I also sort of noticed that, I mean, this is something I just showed you a couple examples and sort of asserted as like a fact without really justification, but the bigger discrepancy, like if these are equal, then they don't spin, little flywheels don't spin. If they're not equal, if they're just off by a little bit, the little flywheels aren't spinning that much, but if I make them off by more, the flywheels will spin more. And so like, that's sort of something I sort of asserted without any sort of justification, but so maybe the discrepancy is kind of what I'm between Q sub X and P sub Y measures the amount of curl. So in fact, like even in this example, Q sub X is 1, P sub Y is 0. And they're spinning counterclockwise. Make them increase the field strength a little bit, and you'll see them spin a little faster, right? They're spinning counterclockwise, which would say that the little circulation around that is positive, because if we're orienting counterclockwise. If I make this negative, they're spinning the other way, right? So I'm even going to say something stronger. Q sub X greater than P sub Y, positive curl. Positive meaning counterclockwise. I'm sort of doing this from one example, which is not good mathematics in general, or not good science or math or whatever, any sort of logic. And if Q sub X is less than P sub Y, it's negative clockwise curl. But today I'm saying just go with me because this is the last day of class and we only have 40 minutes left together. Okay, so and so I'd like to actually I'll be able to justify this though. This is sort of like, if you play around with this for a while, you'll notice these things. Okay, so let me try to give you a little bit of a better definition of curl, and then figure out how we can actually compute it and see where these things come into play. So I said curl is circulation at a point. So one thing you could think about that is like, okay, let's pick some point in the plane, right? Here's some point P. No, I don't use P because that's already a letter that we're using. Point A in the plane. And the circulation around that point, you just take some loop around that point and compute, right? And so we have some vector field, I should say, right? Like we have some, who knows what it's doing, but we have some vector field F in this situation. And then, so the circulation at P, you'd almost say is like the integral of some small loop around P. Or not at P, at A. I don't use P for point. At A equals this the integral f dot dr of C, where C is some small loop around A oriented counterclockwise. The problem is that's not very, there's going to be reasons why this is not a great definition. Because it depends on the size of the loop, right? I mean, I'll get different numbers if I make different size loops. And I want to sort of think about it as a limiting idea, like think about the derivative, right? That's the rate of change at a point. This is a circulation at a point. I really want to make this loop smaller and smaller and smaller until it's just a loop at that, like it almost goes away. What's the problem with that? What happens to the circulation? It'll go to 0, right? If you're just basically integrating over nothing. So it'll go to 0. So that's sort of a problem. And we do something similar. Oh God, I was doing bad zooming today. I didn't stop the share. Sorry, okay. So that's what I wrote just up here. It's not on the top board. So, and take me off screen. Okay, so, right. All right, the circular, so yeah, the problem with this is we can think of it as oh yeah. I could even think of this as like if we take A here as our point and then take this loop around the point A. I could think of something like the circle of radius r, like, you know, and call this C sub r. So C sub r is the loop, is a circle of radius r. R around centered at A. Right, and then the problem is that the limit as r goes to 0 of this is 0. Oh, I used r now twice. Sorry. Very bad. Can we live with that? So that's a problem, right? Because then how do you measure circulation at a point? So it's like measuring the change in a function, right? The change in a function at a point will go to 0. So what do? We divide by something else that goes to 0. We actually have a 0 over 0 situation if we want to get some idea. So instead, one thing you could do if you just wanted to make this like a 0 over 0 and have some sense of what it is, you could divide by the area inside this circle. So instead, compute the integral this circulation over the area inside C sub r. And it turns out now if you let r go to 0, then this is the curl of f at the point A. Okay, so because this is now this is a 0, these both go to 0. And so it's sort of an analog of a derivative actually again. And there's some ratio. So if you want to sort of normalize, like, you know, I mean, maybe it's not obvious that this will work out to be something nice, but it's at least conceptually like an idea of something you could do. I mean, maybe you think maybe we should take the length of the thing instead. So there's question, but I'll show you why this actually works to give us something nice. This is what's going to be the curl at a point. Okay, so this is the sort of the definition. It's you can take the it's the limit as r goes to 0 of this ratio. Okay. Okay. But if I want to make sense of this, like, does this make sense? Not obvious. But at least it's an idea. Not obvious, but let's see. Okay. So in fact, what I want to do is I want to show you that there's some ways to write down circulation that surprisingly, it'll lead to something surprising. Let me do this. So, so let's go back to general circulation for a second. So not necessarily a tiny loop, but just a general circulation. So what I actually want to do is I want to look at something, something like this, so, you know, a wider circulation. What I want to do is I want to go back to a specific case, because this is where this like actually kind of ends up. I don't know, there's a cool computation. There's a neat computation we can do that is sort of not obvious, but you might have to go with me again because of our time constraint as this being the last class, but I don't feel like I can just state for you this. I have to actually do the computation. So let's look at the special case where C is a rectangle. Okay, so I'm just going to draw this. So now it's like, all right, here's my C, like that. So this is C. So this is, maybe I'll say this is the C bottom, the right side. You can think of it as a sum of 4 paths, right? C top, C left. Okay. So C is kind of the whole thing. It's C right plus C top plus C left plus C bottom. Okay. And let me actually even mark this up a little more. Let's say this is like x equals A. This is x equals B. This is y equals little c. And y equals d, okay? I want to actually compute, and so our f is still, you know, pi plus qj. So we've got all these arrows, you know. Who knows? We've got a vector field that we're living in, right? Compute the integral around C of f dot dr. I claim we could actually see some interesting things here. So for example, let's look at the right-hand side, right? Let's look at C sub right. The integral along C sub right f dot dr, well, let's go over here for a second and just think about the parameterization, right? The parameterization is easy. X is always B. And I'm going to use the variable y for the parameter because that's really what's changing. R of t is bi plus yj, right? That would trace this path right there for c less than or equal to t less than or equal to d. No, y. Right? So that's our parameterization of this thing right here. People agree with that? And so our prime is just j, right? And f of r of y, that's how we compute these things, right? So like we plug in, we want to change dr to r prime of y dy. We want to plug in the permutation to f. So what's f of r of y in this case? Well, I guess it's just, well, it's just pi plus qj, but I guess it's p of b comma y I plus q of b comma y j. I'm just plugging in the parameterization for x and y. So there's going to be a lot of letters here. But when we dot these together, and I'll switch the boards in a second. So when we dot these together, we just get this right here, right? Q of b comma y. Okay, is that fair? A lot of letters, but I'm just sort of like trying to do the general. Like I said, I might ask you to just kind of go with me on some good faith because I don't want to run out of time with this. But is that reasonable? So what I'm saying is that the integral c right f dot dr in this case is going to be just the integral of that function from c to d. I mean, you've done some examples like this actually, where like there's a path that was, there's a problem on homework that was a path where it's like you went across and then up. This is kind of just what's happening generally. You're just getting something like this where it's like, oh, it's really just the p function doesn't matter because that's the horizontal component of the vector field and we're going up and down. So only the vertical component of the vector field is going to matter. Is that fair? Okay, similarly, let me just do the integral on the left side. It's going to be all the same, right? Except instead of b, we'll have a. And there's one other thing that's going to be different. What's the difference between the left and the right? How they're tracing the path. Yeah. What's that? Yeah, it's going down, right direction. On the right side, it's going up. On the left side, it's going down. So this is actually the integral from d to c of q of a comma y dy. Right? Because opposite. Because c left is traced in the opposite direction as cy. C left traced in the opposite direction to the c sub right. Okay, so that's c sub left, the integral along c sub left. So this is really negative. It's really negative, the integral from c to d. Q of a y dy. What about c sub bottom? I might do these kind of quickly, just to sort of say like, okay, this is how this works. The integral c sub bottom. So now, you know, the r prime is going to be just I. And so, and you're going to get, so it's really just going to be the p function that you're going to care about. And x is going to go from c to d, but y is going to be fixed. I mean, sorry, x is going to go from a to b, but y is going to be fixed at c along the bottom of the curve. I'm just kind of doing this kind of the fast way. But I think if you set these up carefully enough, you'll see this is like the integral from a to b of p of x comma c, yeah, dx. And one more similarly, the integral along the top, it's sort of like the same relationship as left and right, right? You're tracing it right to left instead. Y equals d here. So it's the integral from b to a of p of x comma d, which is negative the integral from a to b. Okay, so we have these four integrals now. This looks kind of terrible, but there's going to be a payoff. I promise there'll be a payoff. Okay, so the integral around the whole loop is the sum of these four integrals. Is that sort of fair? All right. Well, let's put them all together. Two of the integrals are from a to b, right? And two of the integrals are from c to d. Okay, to erase this. Yeah, that's the part where you may have to take some faith that I'm saying something that's, I'm just doing these computations correctly, but I claim you could go through carefully and write down the parameterizations and get all this. So the integral along the whole thing, this whole rectangle, I'm going to write this as a sum of two integrals because there's the two integrals from a to b. Actually, let me do the two integrals from c to d first. We have the two integrals from c to d. And so we can write that as q of v comma y minus q of a comma y dy if I combine those first two. Plus the integral from a to b of p x comma c minus p of x comma d. Sorry, this is just all letters, I know, but conceptually it's not too bad, I don't think. Now here's the amazing leap of faith, or the amazing thing that you have to just sort of like try to go with or not. I can't really see that board over here. Okay, so here's the amazing leap of faith. Let me just think about an example of something. Like this is like f of b minus f. Like let's just pretend, forget about the y for a second, and just think about something like f of b minus f of a. Actually, I'll even use capital. We've actually just seen something like this with the fundamental theorem of line integrals, right? Expressions like this. I can actually take a difference like this. This is a weird thing because you never think about going this direction. If I see a difference like this, I could write it as the integral of f prime. Right? I mean, that's what the fundamental theorem of calculus says. Certainly right to left. Well, it's funny, I was talking to my other class about this. Like, inequality is supposed to be symmetric, but conceptually it's not really. Usually we start from the right and go to the left. But if you could take an expression like this and see like, oh, I could recognize this as an integral. Why on earth would you ever do that? Well, I'm about to show you why. So in this example, so I claim I can rewrite this thing inside here as an integral, right? And what is it? It's the integral of the derivative. This is like, but it's like an x, it's like an x derivative, right? It's like a partial x because y is, like for any one of these specific, it's like a fixed y, and then we're gonna integrate over all y. So here's the little leap of faith you might have to take with me. Because I claim that this is the same thing as the integral from y equals c to y equals d of the integral from x equals a to x equals b of q sub x dx. we did some sort of like partial integration stuff, right? When we were constructing gradient potential functions, so gradient fields. And yeah, I guess I'm just trying to say that this thing actually does equal this. And it's each specific y, right? This is going to be for each specific y, and then we integrate, we add up over all the y's. Somewhat believable. Okay. Now, what about this one? Well, it's the same thing, right? The integral from x equals a to x equals b. Integral from y equals, now here this is from a to b, so this is actually from d to c. D to c. And now the difference here is going to be the partial y of p. We're integrate the derivative of p, but with respect to y, because that's the thing we're integrating. P sub y. Y. Okay. And now we're almost about to see something amazing. First off, let's see, this, I really should make this, I should really flip this, right? Because this is basically, think about what this is now. It's a double integral. And what is it, a double integral over what region? I guess I have to erase the drawing, but, huh? What? Well, what region is, I just couldn't hear what you're saying. Sorry? The rectangle, it's the inside of the rectangle. This is the same thing as a double integral of the inside of the rectangle, right? Let me switch this and then combine them all. And actually order, well, does order matter? No, not in rectangles. We can switch the order of integration willy-nilly, right? So this is actually, let me write a couple more times. So this is the integral from c to d, integral from a to b, q sub x dA. I'm going to switch the order here. So this is minus the integral from a to b, integral from c to d, p sub y dA. What was I talking about earlier about when there's circulation and when there's not? When q sub x equals p sub y. I just got q sub x and p sub y inside an integral, inside a double integral. So in fact, yeah, I mean, you really should have been excited when these showed up because we've been talking about these, right? It wasn't q sub y, it wasn't p sub x, it was actually q sub x and p sub y. And we're getting the difference. So this is the integral over the entire the inside of the rectangle. So it's really a double integral. This is where I almost want to write like a double integral because it's really like I want to, but you know, let's just go with what the book does. Of q sub x minus p sub y dA. And this is the thing that's amazing. We turned this single integral, this line integral, into a double integral. And it's exactly the thing I was talking about, the discrepancy between q sub x and p sub y. That's exactly what you're doing. You're integrating that over the whole region, right? So, because for example, if this vector field was conservative, path independent, circulation free, what would this integral be? 0. And that agrees with this, right? Q sub x minus p sub y also 0. And I said, but I was saying like if this is, yeah, like if this is positive, right, so it's really going to, this is really the discrepancy. This is what I was seeing. Discrepancy. It's a word, right? It's basically the difference between two things. Fancy way of saying the difference. So what I'm saying is the integral over the boundary of the rectangle equals the double integral over the inside of the curl. That's really what we said was, well, okay, I actually didn't say that was the curl. But I want to justify to you that that really is the curl also. Okay, so that was a big long computation just to try to get to this idea that somehow, oh wow, we can actually see the q sub x and the p sub y coming out of something, and that's kind of amazing. So, i.e., given a vector field F defined on a region R, I should say F equals Pi plus Qj defined on a region R. Now it turns out that it didn't matter if it was a rectangle. It actually works on any, you can sort of show it works. You can estimate any region with rectangles. And so you can actually show that this works over any loop. Defined on and in, let me say on and inside the closed loop C, then the integral around the boundary, again, this means counterclockwise, is the double integral. I always want to write. Okay, I'm just gonna have a look. The double integral of inside of C of Q sub x minus P sub y dA. And this is what's called Green's theorem. Like kind of amazingly, you can turn a single integral into a double integral. Okay, that makes sense. And yeah, I mean, I could justify that it's like works for things beyond just rectangles, but it's kind of amazing. Sometimes people write this as, instead of just like, so like here's the loop C. Do whatever you want. You could think of this inside as, some people will call this like R for the region inside. So I could put R right here. And then actually, sometimes the C is written as the boundary of R, where you're supposed to read that delta as boundary. So you could also write boundary R here. And where it's given that the boundary is going to be oriented counterclockwise. So back to the curl idea. Curl of F at the point, I've been using capital A, but let's just say at the point x comma y, we said was the limit as r goes to 0 of the integral along CR f dot dr over the area inside C sub r, right? But now what we can do is we can use Green's theorem to replace this numerator with a double integral. So I can say that's the limit. And now the bottom is still the area inside C sub r. The double integral along the inside of C sub r of Q sub x minus P sub y dA. See, I keep wanting to write double integral there, just because it's like two integral signs. By the way, the handout now I can actually show you on screen because it has this statement. And now here's the thing. If this is a tiny loop, we can really pretend Q sub x minus P sub y is basically constant because we're near a point. Is that fair? Like we're close to a point. So this is approximately constant. Near x comma y, because we're if r is small, i.e. r is small, then we're really just near this point. So we treat this as a constant. What can we do with a constant inside an integral? Pull it out. If we pull it out, right, if we're going to treat this as constant, this is just like 7, and we pull it out, then what do we really get? We just get the integral of dA. What's the integral of dA? What's the integral of a region? Like the integral of 1 over a region. It's the area, right? It's the area. So in fact, the areas cancel, and you just get this expression, is my point. Oh, that's exciting, right? So you actually get, so really the curl is q sub x minus p sub y. So sorry, I know it was a long road to go down, but that was kind of the, yeah, the exciting point. The Green's theorem, and then that this idea that it really is the difference between q sub x and p sub y that determines the amount of the little spinnies, to use a technical term. So then the integral, right, the integral of the inside of c sub r, q sub x minus p sub y, is in fact q sub x minus p sub y times the integral inside dA, which is q sub x minus p sub y times the area inside c sub r. So the curl of f at this point is actually the limit as r goes to 0 of q sub x minus p sub y times the area divided by the area. Those cancel and you just get, so you get the curl is q sub x minus p sub y. And that's kind of cool that we can actually measure. So I wasn't lying when I was saying like this expression, the discrepancy really measures the amount of spin. It's kind of neat. Cool. That was a lot. Trying to fit it in the last class. But so I wanted to connect it to the little spinny things because I think that's the coolest thing to do. But yeah, there's the spinny things again. So it's like I said, if I make, so this is really, I mean, you can do, again, I can make the fields. If I did 2y here or something. Whoa. Q sub x is, no, sorry, let me share screen. Q sub x is -1, p sub y is 2, so q sub x minus p sub y is -3. And notice these are spinning counterclockwise. I'm sorry, they're spinning clockwise, which is negative circulation, negative curl. Counterclockwise is always going to the positive direction. If I change this all of a sudden to 3, whoa. It's hard to see. Are they spinning counterclockwise? Look at the ones near the middle. They are spinning counterclockwise because now q sub x is 3 and p sub y is 2, so the difference is +1. Maybe they're spinning a little faster because now q sub x minus p sub y is 2. Make sense? Okay. Wait, hold on a second. Let me go back to the, let me just say a couple of things. So, just because we're going to run out of time here. Which is very sad. I told you we could keep going through like February if you want. Yeah, so one thing, there's different ways to use this, by the way. So like, for example, if I gave you like a really horribly ugly vector field, the thing you might want to check, but it's over a closed loop. So here's a closed loop. What is q sub x for this vector field? It's nice, it's 5, right? All the badness is in the y over here. What's p sub y of this vector field? 2. So this looks like a horrible line integral, but it's really just the double integral of 5 minus 2 over the inside of this circle, which is 3 times the area of the circle. So it's 3 times pi r squared, 12 pi. So we just gave the answer is 12 pi. 3 times 5 minus 2 is 3 times the area of the circle radius 2 is 4 pi. So there we go. We just answered this by sight. So Green's theorem can be helpful. That's contrived. But the other thing that I sort of wish I had time to do, which is we kind of ran out of time, is if you actually do you pick some specific vector fields like these. Q sub x minus p sub y for each of them is 1. This is q sub x is just 1 minus p sub y is 0. Q sub x is 0 minus p sub y is -1. Q sub x is a half minus negative a half. That you can actually use these to compute area. So you can actually do a line integral. So this is going backwards. This is going from the double integral. If I want to find the area, sometimes you can actually compute a line integral around the boundary. And it will tell you the area, which is kind of amazing. And there's actually devices you can buy called phonimeters that you could like, I could like roll it. It's like something you take and you like roll it around the edge of like a table or something. And when you get back where you started, you press the button once, you like go around it, and you press it again, and it tells you the area that it's enclosed. And that's actually uses Green's theorem to figure that out. It's kind of neat. There were like actually physical ones that people built back in the day, and now there's like digital ones you can buy. I thought about trying to get the department to buy one, but they're like $2,000 or something. So I don't know. The department hasn't decided not to buy one. So anyways, so this stuff's very cool. There's a lot more math here. I mean, but this is about usually what I get through. So I mean, this semester has been weird. All the professors have been talking about how we didn't really cover necessarily as much material as we have in the past. But I usually finish with Green's theorem. And there's a lot of cool. Go read chapters 19, 20, and 21 for over break, just for fun. And you can learn some more stuff. So, all right, everyone. Thank you. That was fun. Test is online. I'll post my office hours. And I will hopefully see a bunch of you in the next few days. And just email me if you have questions and stuff. So, all right, thanks. Yeah, no, it was good. Yeah, thanks. No, it's great having you. I appreciate you